One of the hardest parts about Exam 2's material is being able to decide when and where you're supposed to use a certain type of reaction. SN1, SN2, E1, E2, there are a lot of rules behind each of these reactions and it can get very confusing very fast. So the purpose of this video is to try and distill all that information and make it very clear when and where you're going to be using these individual reaction types. And to do that, we're going to answer 3 key questions. Question 1, is what's over the arrow negative or neutral? And why does that matter? Let's take, for example, over the arrow we have OH minus and we compare it to H2O. So the difference is just a matter of a proton, a matter of a negative charge versus being neutral. Well, what we have taught you is that substitution 2 and elimination 2 involve strong reactants, strong nucleophiles in the case of substitution 2 and strong bases in the case of elimination 2. Whereas the SN1 and E1 pathways involve weak reactants. Now, how do we tell if something's strong or weak? Well, think about it. If you're a nucleophile and you want to be strong, or if you're a base and you want to be strong, you want to have your electrons ready to go out and grab protons or attack leaving groups, and that means you need to have those electrons on you at all times. Well, which of these two has a greater source of electrons? Definitely the one that's negative. If you're negative, that means you have an extra set of electrons, and that's definitely going to make you stronger and more reactive. So if you ever see a negative charged reactant over your arrow, most likely it's going to be following either an SN2 or an E2 pathway. It is a strong reactant. It could be either a nucleophile or base, and there's a little more context to figure out when and where it's going to be one or the other. But for now, we're just going to say strong reactant, which means it's going to be SN2 or E2. And if you're neutral, and in some cases positive, well, that makes you weak. You're not nearly as reactive because you don't have that negative charge to go out and make bonds or grab protons. So that means you're going to be following an SN1 or E1 pathway. And right off the bat, now we've cut our options down to half. We are either going to be SN2 and E2 or SN1 or E1. Now let's go further with, let's say the answer to this question was it's negative. How do we differentiate whether it's SN2 or E2? So we see our reactant's negative, and now we're going to start figuring out, well, is it SN2 or E2? Now the first thing to point out is number 1. What degree of carbon is the leaving group on? We have taught you that SN2 reactions are super sensitive to steric hindrance. And what that means for you is if you have a leaving group on a tertiary carbon, meaning a carbon with 1, 2, 3 other bonds to carbon, it can never undergo SN2. SN2 cannot occur on tertiary leaving groups. Secondary leaving groups and primary leaving groups can still undergo SN2, and there are certain conditions that tell you one versus the other. So let's talk about some good nucleophiles and good bases in the context of SN2 and E2. So first of all, some reactants that very much are much better nucleophiles than bases, meaning they much more prefer doing SN2. We have all of our halogens. If you see Br minus, iodine minus, chlorine minus, I'm going to leave fluorine out because it kind of does a bunch of other things we don't like, so we'll ignore that. But most other halogens are super, super good nucleophiles and pretty terrible bases. So they much prefer doing SN2 as long as you're not on a tertiary leaving group. Other super good nucleophiles that much prefer doing SN2, anything involving sulfur, and most commonly on the second exam that would be either SCH3 minus or SH minus. 2 other ones, C triple bond N. We write it CN for short, but there's actually a triple bond connecting those 2 atoms. And finally, a weird one, N3 minus. We don't really use it for anything until Orgo 2. Just know that it's a good nucleophile because sometimes you'll see it in a question. Now, one key point to make is these are all negative because we said, yes, they are negative. That means they're going to be either SN2 or E2. But very often you'll see them written out as neutral as NaN3, for example, or KCN. They look neutral now. Doesn't that mean they're weak? Remember, both sodium and potassium are metals, and when they couple with a nonmetal, there's an ionic bond. We know that the metal, the sodium, is positive, or in this case the potassium is positive, and that means the thing that it's attached to is negative. So whenever you see a sodium or a potassium on something, you can treat it as if it's negative. Okay. Now, these are things that preferentially do SN2. If you have a primary or a secondary leaving group, these will most likely undergo an SN2 pathway. If you have a tertiary leaving group, well, since tertiary leaving groups can't do SN2, then maybe these will act as bases and do E2. But I still am wondering about that. Most commonly, I haven't seen those given in a situation like that. Now, there are certain molecules that are both good bases and good nucleophiles, and then it comes down to the degree of your leaving group. So what about the molecules that can do both SN2 and E2? Well, those reactants are your O minuses. So OH minus, OCH3 minus, OET minus, and really any O minus that's on a carbon chain. So it could be a long chain, a short chain, doesn't matter. These can act as good nucleophiles or good bases, but how do we know when it's going to be one or the other? Well, the rule of thumb that we use is it will be SN2 if your leaving group is primary. These guys are super strong bases, but if there's very little getting in the way of them coming in to replace that leaving group, they will. But the second you toss in a little bit of steric hindrance, you put that leaving group onto a secondary or tertiary position, then you're going to switch over to the E2 pathway, meaning these will now act as bases and make double bonds by pulling off protons. There's one other molecule on this list that falls into this category, a carbon-carbon triple bond minus. These also will do SN2 only if you have a primary leaving group, and do E2 whenever you have secondary or tertiary leaving groups. Okay. Finally, what reactant will only ever do elimination 2? Well, we teach you about 2 of them. These are super strong bases that are sterically hindered, your bulky bases, namely terbutoxide, O minus with a chicken foot on it, a terp-butyl group. And there are a bunch of ways we can write this guy out. The most common and confusing way they write it, though, is OC parentheses CH3 parentheses 3. This is the molecular formula of what I've drawn here. But they can also write it TBUO, or just spell out the full name, tert-but-oxide. Either way, this is a bulky, sterically hindered base that never, ever, ever does SN2, at least in Orgo 1. In Orgo 2, there's one question where we make it do that, and you can call us liars when you see that. But for now, only does E2. The other one that we talk about occasionally is LDA. And what LDA looks like is a nitrogen with 2 isopropyl groups coming off of it that's negative. And again, we have these big branchy groups that get in the way of the nitrogen coming in. So it can only grab small things like protons. It can't attack a carbon with a leaving group. So both terbutoxide and LDA only do elimination 2 as far as you're concerned. So when you're given a question and you see that the thing over the arrow is negative, try and see if it matches up with one of these reactants. If it's a matter of these, then you know it's most likely going to be SN2, so long as your leaving group isn't tertiary. And if you have a secondary or tertiary leaving group, in the case of any of these, then you're probably going to have to decide, well, is it SN2 or E2? Primary leaving groups will do SN2 with these, and tertiary and secondaries will do E2. And then these will always be E2. Now, let's go back to question 1. What if our reactants were neutral? What if we were going to do an SN1 or E1 pathway? How do we tell those two apart? Well, admittedly, unlike the SN2 and E2 pathway, which have very clear winners for reactants, it's a lot harder to tell E1 from SN1. And so usually there will be a little extra context in the question to help you differentiate. The first and most important thing to recognize is if the word heat is given on the arrow. The second you see the word heat over the arrow, you know that this reaction is going to be elimination. Okay, so if you ever see the word heat, you know you're doing elimination. Now, sometimes instead of heat, they'll write delta, or they'll write high energy, a high energy system. But most commonly, they write heat. The point is, it takes a lot of energy to make that double bond, because the double bond ends up making a more stable product in the end. So you need those higher temperatures, that greater energy system, to allow it to occur. Now, what if they didn't tell us heat? There's another way they can hint at the fact that your reaction is following an E1 versus an SN1 pathway. Let's take, for example, I gave you a structure that looks like this, with a bromine sticking off that secondary carbon, and I tell you the product of this reaction with H2O is C4H8. What reaction am I doing? Well, first I answer the question, is it negative or neutral? It's neutral, so I know it's SN1 or E1. Now I ask what degree of carbon is the leaving group on? Secondary. Well, that doesn't favor E1 versus SN1 in any degree. So now I ask, is my reactant a nucleophile or a base? Still can't really tell, it's one or the other. So I look at my molecular formula. And what do I see? Did I do a substitution where I replaced my bromine with what's over the arrow? Or did I make a double bond? If you check your IHD formula for these two, you'd find that the IHD of this one is equal to 1. And that means it has either one double bond or one ring. And well, I don't think we're making a ring here, so it must be a double bond. We increase the IHD by 1, because this has an IHD of 0. I lost the bromine, I increased the IHD by 1, and it didn't get anything else. This reaction right here must be elimination 1. Let's look at a different arrow. Again, I'm going to give you H2O. H2O is capable of doing E1 or SN1. But my molecular formula of the product says C4H10O. Well, now I have gone from something with bromine to something containing an oxygen. I have substituted that bromine for an oxygen, so this must be my SN1 pathway. And if I check my IHD is still 0. So here is a second way that they can tell you SN1 from E1. They either tell you heat, or they'll give you a molecular formula where it's clearly been either substituted or eliminated. Okay? Now, before I forget, what reactants typically undergo the SN1 or the E1 pathway? Remember our list of things, oh, actually, I'll just write it out. So, most common reactants for SN1 and E1 reactions are H2O, HOCH3, HOET. These are the three most common I see. And notice, I'm saying that these react for both SN1 and E1. That's why it's kind of hard to tell them apart. You don't have that nice list like we did for SN2 versus E2. So it really comes down to the context of the question, and these are the things you should be looking out for. And if you're good with that, I think you'll have a much easier time telling E1 from SN1, SN2 from E2, and the 2s from the 1s. And with that, I wish you the best of luck on exam 2.